Hello, everyone, and welcome to the VAS webinar, Manure Matters, Analysis, Management, and Trends. I'm Catherine Garcia, and I will be your moderator for this webinar. A quick note, many of you have known us as AgSource Laboratories, and in 2020, we joined with our sister company and now operate under the name VAS. Together with their agricultural software expertise like DairyComp, under the VAS Pulse platform and our state-of-the-art laboratory equipment and extensive amounts of data, we have so much to provide our valued clients and now and into the future. We'd like to take a moment for you to get familiar with the Zoom webinar controls. Locate the chat and Q&A buttons at the bottom of the screen. This is where you can submit questions along the way for our presenters to address at the end of the webinar with time permitting. Any questions that we're not able to get to live will be responded to via email. Note, we will be recording this webinar. We'll be sharing the link afterwards in an email, so watch your inbox for the follow-up email with exclusive manure resources for you to ramp up your manure testing program. Finally, when you exit the webinar, we would appreciate your participation in a short survey that will pop up, just asking us how we did and your suggestions on possibly what webinars you would like to see from us in the future. So before we get started, I'd like to introduce our presenters. Our first presenter is going to be Dr. Jim Friedericks. He has been with VAS for 9 years. Dr. Friedericks received his PhD in soil science from Virginia Tech University. Our second presenter is Mrs. Haley Sand. She has been with VAS for 6 years. She received her master's at UW-Madison, and she is CCA certified in Wisconsin and Minnesota, as well as 4R certified. So thank you to both of our presenters. I'd like to now turn it over to Dr. Jim Friedericks to begin our webinar.
Welcome. I'm Jim Friedericks. I'm pleased to be here and talking about manure management. The focus this morning is on manure management as nutrient management. And so whether you're using manure as nutrients for fertilizer, as fertilizer source for nutrients in your crop production, whether it's cash crop or feed for your livestock production, how you manage those nutrients is important. And it's actually an opportunity to receive some economic return on the farm from good management practices. So those nutrients have value. That value can come back to you and reduce fertilizer costs. Also, manure is a waste. It comes from the byproduct of feeding animals. And so, of course, it needs to be managed as a waste, but it's better to utilize it as a nutrient source rather than to dispose of it as a waste. It may cause harm to the environment. So how you manage these nutrients is important. Of course, because it is manure, it's a highly variable material. It has a lot of moisture, which makes the density of the nutrients in the manure often very low, depending on the moisture content. That content can be variable depending on where that manure comes from, the livestock that produce it, as well as the way that manure is handled in the collection system. Different distribution processes, whether you place it on the soil surface or incorporate it in the soil, and how you transport it to the field, these are all concerns that also impact the good use of the manure and its maximum benefit back to the farm. And as I said, it's also a potential source of detriment for the environment. So managing it, making sure you don't have over application or spills is also important in how we control manure applications and do it for good purposes. Managing this manure is a requirement for good crop production. It's a best management practice if you have manure source to use it to maximize your crop production, but it's also in many states and in Wisconsin specifically, we'll talk about required by law to manage these nutrients according to the directives of the state. And so you have to follow those considerations as well. So the quality that of the manure has needs to be evaluated. It varies from site to site, from one pit or one barn to another, whether it's indoors or outdoors, how it's stored, and also how the manure within that stored facility or storage tank also varies from top to bottom. And so those are considerations that need to be evaluated, as well as the application of manure when it's applied, how much labor is required in the application process, when it's incorporated, and how quickly it can be incorporated. These are all big concerns in managing manure. And so I want to look at that, but one of the criteria that I'm specifically looking at is the nutrient content. And so without sending a sample to the laboratory, there's estimates of what the manure contains, but really knowing what's in that manure requires an analysis that's performed in the laboratory. So that'll be the focus primarily of what I'm talking about. VAS has 6 laboratories in the northern states of the United States. Of those 6, 2 perform manure analyses. One is in Wisconsin at Bonduelle, and they focus primarily on dairy samples. The other is in Ellsworth, Iowa, and they focus primarily on swine manure samples. That's because of the industries that are there, and that's generally been the historical focus of those labs. To learn more about the laboratories, you can look at the vas.com website and select manure testing as the option to explore. What's in a manure test? Usually, always it contains a dry matter analysis, a nitrogen analysis, and a phosphorus and potassium analysis. Our laboratories also include sulfur in that. So those 5 tests are the typical minimum amount. You can add to that, to the nitrogen, you can add an ammonium and a nitrate analysis. You can also add the secondary nutrients, calcium, magnesium, sodium, or the micronutrients, copper, iron, manganese, and zinc. Additionally, you can test the manure for soluble salts, which is done by conductivity test, and measure pH. It's important to know salt content just to know how much salt you're adding to the soil year after year if you continue to apply manure in the same location. Here is examples of the 2 reports from the 2 different laboratories. On the left is the report from Ellsworth. It's a very busy report. I recognize that. It is a complete analysis, so all the data that we do is there. Just to highlight, next to the name of the analysis, there's a results column of the material as received. So if it's a liquid sample or a dry sample, it's represented there as % of the sample that we received. And then it's also presented in liquid and dry format in pounds per 1,000 gallons or pounds per ton, depending on how the material will be applied to the field. The units are appropriate for that application method. On the right is a typical report from the Bonduelle laboratory, again with nutrient content, total nutrient contents for NP and K and sulfur in pounds per ton in this case. And they present their data just in terms of the type of manure it is. If it's solid, it's presented as pounds per ton. If it's liquid, it's presented in pounds per 1,000 gallons. There's also average values. So there are publications that you can look up manure, the type of manure that you have, and see what kind of dry matter distribution there you can expect, and what the nutrient content is of that dry matter for that type of manure. So you can see the dairy, the beef, swine listed there at the top for liquid, and the solids, dairy, beef, chicken, and turkey litter at the bottom. This data is from a compilation of some results, extension publications actually, from Minnesota, Iowa, a couple other Midwest states, as well as a couple of states in the Southeast, and from Alberta and Canada. So it's just an average data set that I put together to show the ranges that we see in manure analyses and what's typically expected. This next slide shows similar data, but this is just from the Wisconsin laboratory in Marshfield. They've compiled their data over a period of time, and then presenting that in pounds per 1,000 gallons or pounds per ton, rather than percentages like I did in the other one. But again, showing the difference between liquid and dry and what you can expect in material that you handle and what you're going to be applying in the field. So I will compare our data, the analytical data, to these 2 tables, and I'll explain that as we go through the data. Sampling manure is an important aspect of collecting the sample, and Haley is going to just talk a little bit about that sampling process.
Thank you, Jim. So when collecting manure samples, timing is everything. So schedule your sampling early, preferably before you begin field work each season, so in the fall and in the spring. Allow for time to sample, ship, and receive those results as well. Manure in a pit and stockpile fairly stable over time. Samples can be frozen for storage in between actually physically sampling and getting them to the lab. So when it comes to collection, accurate results start with a representative sample. Composite or representative samples consist of 10 to 15 subsamples. So depending on your manure type, if you have like a solid, sample different locations in a stack, or sample different loads and or different points within each load. When it comes to liquid manure in a pit, we suggest agitating the pit 2 to 4 hours before sampling, and then collect from several points as well as depths within the pit. And then if you're not looking to agitate, there's a really neat tool that I'm going to talk about here shortly, but collect several profile samples or several samples from different levels within the pit, put it in a bucket, mix it up, and then there's going to be your sample. So here is that profile probe that I was talking about. We have the little zigzag line on the picture because this is a cropped photo. The tool is actually approximately 10 feet long, and it acts kind of like a straw. So when you have a cup and you put a straw in the cup, you're collecting the liquid in the straw, and then you plug it, lift it out, and you kind of have a sample of your solution. Same thing here. We have the plug at the bottom though. So you'd stick it in the manure while it's open. Very slowly, you would end up plugging it or lifting the handle at the end and then pulling it out. And again, take approximately 10 cores throughout your manure pit for a composite sample. When it comes to handling, we need to remember that manure is biologically active and will change in the sample bottle if it's at the right temperature. So if you can cool the sample as quickly as possible or even freeze, that's even better. If you are dealing with unfrozen samples, we suggest getting those to the lab as soon as possible, and same day is preferred. And we have these sample jars, which are pictured to the right. That's what we suggest that the manure samples come in. We absolutely cannot take glass bottles or plastic soda bottles. Those will be refused, and we'll ask for another sample. So filling out the submission sheet, the more information you can put on here, the better. Date collected, location, manure type, handling method. At the bottom, you can select which analysis you want done, dry matter only, if you want a composite or like all of the nutrients kind of a thing, or if you just want select nutrients, that's all on the sheet. Bare minimum, like at least get your contact info on there so the lab can call and say, hey, what do you want done with your results? Or if we can't read it.
Thank you, Haley. So we do have one more poll question that we're going to launch, and we want to know, do you currently sample your manure? The options are yes, sometimes, no, I only use the book values. Why do I need to sample my manure? Okay, thank you, everyone. So it looks like 42% of you are saying yes, and 45% of you are sometimes, and about 12% are they only use the book values. So I'm going to turn it back over to Haley, or excuse me, back over to Jim to actually talk about that manure analysis.
Well, it's good to see from the poll that nobody wonders why you have to sample your manure now, perform a manure analysis, because that's the focus of what I want to talk about, the manure analysis. We have the two laboratories, as I mentioned, and the data I'll be presenting is a compilation of 3 years of data from both laboratories, 2018, 2019, and 20. And combining all those data, most of the dairy, again, is from the Wisconsin lab, and 51% of those samples are dairy. And then the other large component is the swine or hog manure samples from Ellsworth, and 36% of those are swine manure samples. We do get other samples. We do test a variety of manure types. 5% or so of their samples that we do analyze are cattle, and most of those come from other states. And then we also test poultry. A large part of that comes from Iowa, but it represents a very small component or portion of our total in the sample analyses. Of the samples you get, as you see these bottles in the foreground of the picture, most of the samples, 75%, come in as liquid. And we have a way of homogenizing the sample as we receive it, and then performing an analysis on that liquid. The dry or solid samples, we also can either dry them down and analyze the micronutrients or process them in a fresh state for the nitrogen components. So the manure analysis is important because you don't know really what you have unless you analyze it. If you just go with book values, you may or may not have, excuse me, a representative value for the manure that you are sending in. So it's important to analyze it and get the exact results of that analysis. The dairy samples that we've analyzed, again, come from Wisconsin, and you can see from this distribution of the dry matter. So what's represented here is the percent of the total number of samples that we received that fall within that dry matter air column. So from 3 to 4% or 4 to 5%, you can see that they're above 10%. They represent more than 10% of the total number of samples in that total spectrum of what we've gotten in. 71% of all the samples we get tested as liquids, which means they're less than 12% dry matter. That distribution is, again, there on the left, but what I'm showing on the right here is the distribution of total nitrogen in all those samples that are analyzed from dairy, whether they're liquid or dry. You can see, other than that cloud that goes up to around 100 pounds per 1,000 gallons, there's a high concentration down in the lower left corner, and then that sort of spreads out as you move to more and more dry matter in that batch of samples. Looking at that same data set then on the left here, but I'm just focusing on the 12% moisture content, 12% dry matter content of these dairy samples to look at the nitrogen that's there. You can see the distribution in that scatter graph, and then down below that is a chart with some graphs and bars that represent what we're actually analyzing. The lines are the lines of the analysis for the samples that we processed in the laboratory. The orange line represents 25%, and the yellow line represents 75%. What that means, at 25% of the samples fall below that line, so they have less than that amount of nitrogen for that moisture content or dry matter content. And then 75% means 75% or have less than that amount within there. So really the significant thing is the area between 25 and 75 represents 50% of all the samples that we analyzed. So those parallel lines are nearly parallel lines at each dry matter content represent how much the average or the expected nitrogen content for our samples that we processed in these 3 years. The gray is that median line, which is exactly 50%. The blue is an average line. And notice that the blue is kind of goes out of bounds there at 2 to 4% dry matter. And that's because there's a higher concentration of nitrogen in some parts, some of those samples that bias that data. So be careful when you consider average data, because it can be biased by outliers, whereas the median value shows you half the samples are above this and half the samples are below this, and this is what you expect. The closer the average and the median lines are, the more homogeneous the sample set is, and the more trust you can have in that average value. The bars in this case, the columns, bars, represent those graphs or those tables that I showed, the book values. The blue one is the compilation of several states and the expected nitrogen content for each of those dry matter sets. And the green represents that data from Wisconsin. So the data is not consistent on all of them. Usually it's fairly close, but sometimes there's a different value between the average value over a larger geographic area and what Wisconsin is finding and expecting from their samples in their analyses. So to summarize that, for nitrogen, our data looks fairly consistent with expected values, particularly at the low end at 1 to 2% dry matter, where the bars and the data are quite close together. At the high end at 6% and above, it looks like the book value may be overestimating the amount of nitrogen that we're finding in the samples that we processed. On the right side of the image here is the phosphorus availability. The bars and the lines mean exactly the same thing. You can see the distribution in the scattergram above that. What is interesting of this is that the phosphorus book values from a variety of states is quite high compared to what we're finding and what the Wisconsin data set is also expecting. So it's important then, from that you can see that if I just use book values, I may be way overestimating the amount of phosphorus that's available in the samples compared to what's actually analyzed in the laboratory. The next slide here, we have K2O or potash on the left and sulfur on the right. Looking at those graphs at the bottom, very similar trends, increasing as you get into higher dry matter content. The variability is a little bit wider for potassium, just because potassium is more variable. And the expected values from the book values are fairly close to what we're finding in our laboratory analyses. That's also true at the lower dry matter contents for the sulfur, but at higher dry matter content, it looks like Wisconsin is underestimating the amount of sulfur there, and the book values are overestimating it. So again, if you don't test it, you don't really know unless you have that analytical result. Next, we'll look at beef cattle manure. Although it's a smaller component of our total analyses, some of the relationships are very similar and important to look at. The difference with beef cattle is more of the samples are dry. About 86% of the samples that we receive come in 20% or well, at least more than 15% dry matter content. And so their way they're going to be handled in the field is different, depending, just because they're a drier sample. The analytical results for nitrogen of that set, you can see the liquid portion is there in the lower left, very concentrated set of dots, and very similar to what we saw for the nitrogen in the dairy samples. But because more of the samples are dry samples, you can see that the importance of that, especially from 20 to 40, there's a lot of samples in that range. And then the variability increases as you get farther and farther into drier manure samples. So here's the presentation of the nitrogen on the left. That same spectrum, again, here I'm looking at all the samples. And above on the right side, we see the liquid content in terms of pounds per 1,000 gallons. And you can see the book value and the Wisconsin values highlighted in the columns, as well as the ranges that we found in our analyses. Fairly consistent, fairly tight distribution at the lower moisture contents. When you start getting higher dry matter content, at low dry matter content is very tight. As the dry matter increases, the variability increases. The bottom part of that graph shows nitrogen variability in the dry sample in pounds per ton. And you can see, again, those lines are fairly far apart, and the average is consistent with the mean, but the difference between 25% and 75% can be as much as from 10 to 17 pounds per ton. And so that's a fairly wide distribution of nitrogen in a sample. You don't know until you test it, as I said, and it looks like the expected values are fairly close to that, but maybe could be higher than it actually is. For phosphorus, same kind of presentation here. The liquid on the upper end, tighter at low dry matter contents, and as you get higher dry matter content, the distribution gets wider and wider. And under the dry sample analysis or report, you can see that just continues. For the drier the sample, the wider that distribution becomes. Again, anywhere from 6 to 14 pounds per ton phosphorus or P2O5. That's a lot. That's a lot of variability. You could be vastly over applying the amount of phosphorus based on what the book value is or what you assume your sample is if you don't analyze it. For potassium, similar trends, increasing as you go to drier and drier samples. Looks like our book values and the analytical results for liquid are fairly consistent, as well as in the dry sample. It's a little bit more variable, but the book values are predictive of what we were seeing as well. Sulfur analysis on the beef cattle is follows the same trends. Sulfur tends to follow the same pattern as nitrogen, so you see that increasing as you go to the right, and as you get more variability as you get into drier samples. I do want to point out here two things. One, the expected values from both Wisconsin and the book on the dry samples are considerably lower than what we're finding. And the median value is one to look at here rather than the average. You see that average line is way above the 75% line. And that's because of this scatter of samples that you see on the left in the scattergram. It's like a column right between 40 and 60, where there's numbers that go up to 450 pounds per ton. That's a lot of sulfur. And those samples originated from two locations where it appears that the manure is being supplemented with some sulfur to get sulfur out into the field. It's a practice that does happen if you're making recommendations for somebody to apply their their manure. Know what the sulfur is, because some places do supplement it. And I talk about this again with the swine manure as we get farther along. Poultry manure, most of the samples that come into the laboratory are dry, 79% or higher than that 12% moisture content. We do have this little spike over on the left at less than 1% dry matter. Those are samples from the lagoons where they collect the water from the egg wash stations and the truck washout stations. And that's a waste management issue rather than a manure management issue. So they have to test it in order to know what they're applying as a DNR waste management requirement. Looking at the nitrogen, we see the distribution of nitrogen also going up and going wider as you go to the right with more and more dry matter. And I'll present that in the next slide. It presents it as on a dry matter basis. Basically, not looking at the liquid samples because they're anomalies, but the table or the graph at the bottom shows the distribution of those nitrogen samples. A little bit wider distribution. Remember, it's not as large a data set as we had for the dairy, and so there's going to be more variability just from a smaller data set. But the averages and the means tend to agree fairly well, as do the book values, maybe a little bit high, but falling within that 50% line, especially at higher dry matter contents. For phosphorus, that's not so true. The book values underestimate the amount of phosphorus that is available in these poultry samples. And so again, if you don't test it, you don't really know. But there is a lot of variability there. And if you just look at the book values, you could be quite a ways off of what you're actually applying to the field. Potassium, the trends are consistent with book values. The variability is as expected. And from the sulfur analysis, you can see that the sulfur at the low end is also fairly high compared to the Wisconsin values, but the book values from the other states fairly well predict what you see at the 80 to 100% dry matter content. So there is variability, but it's not more than expected and is consistent with what you expect from the book. Finally, we get to swine manure. In Iowa, virtually all the samples that come to the laboratory are liquid. 96% of those samples come in, and we see very few that are maybe a little bit higher dry matter content, but are still liquid enough, depending on how they're managed in the field. 20% moisture, you may have to apply them as a solid rather than as a liquid. But most of them are liquids. The distribution of nitrogen of those samples, very concentrated in that lower left corner of the scatter graph, and up to 20% of the 20% dry matter will describe almost everything that we have in the samples. From a distribution of that variability, again, a nice tight distribution of the samples, good data set that you can see the lines are quite parallel. And then the bar graphs are just a little bit lower than what we're finding in the laboratory, but fairly close, and could be used as an application guideline for nitrogen. For phosphorus, that's not always the case. At the higher dry matter contents, the book values from the variety of states is overestimating the amount of phosphorus that's there. And Wisconsin looks like it actually underestimates it, but is much better at predicting that lower phosphorus content than the average book values over a larger geographic area. Again, fairly tight data, but good distribution. Potassium, again, the distribution is a very tight distribution. And in this case, the laboratories are finding that there's more potassium available in that manure sample than any of the book values predict. And so it's not one of the limiting factors in terms of how much can be applied because of regulations, but it is a nutrient that is required by crops. And so over application of something that you're not crediting economically would be a waste of money to apply it without knowing that you're applying that much potassium in the field. The phosphorus availability or variability is, again, similar to the nitrogen, and it looks like we're finding a bit more sulfur in the sample than there is expected, especially in the Wisconsin data set. And again, if you look at the scatter graph, there's that cloud of samples that are above the norm. And this I know is from samples where the pits have been supplemented with a sulfur-containing nutrient solution, so that when you apply it in the field, there's a bump in sulfur that goes out to the field. So there's plenty of sulfur there. But again, if you are not aware of this supplemental sulfur that's added, you may be not accounting for everything that's going into the field. So as consultants, which many of you are, it's good to know this, and you won't know it unless you test the sample and find out what's exactly going on in the sample. Nutrient availability is a tricky thing because, particularly for nitrogen, because the nitrogen that's applied as manure is not all immediately available. It has to go through biological processes, some of it, to become available. And so that is, it's handled differently in different states, and it's handled differently from liquid and dry samples. In this figure, you see the results of the analysis for a liquid hog manure sample. And you can see that in the first year, the amount of the amount of nitrogen, total nitrogen available is up to 56 pounds per 1,000 gallons, which is the pounds per 1,000 gallons of the material. But there's a range 49 to 56%. If it's injected. If it's incorporated, that range goes down a little bit, 48 to 55%. And if it's broadcast and left on the surface, then it's considerably lower, 37 to 50%. That is following the guidelines of hog manure application in Iowa. And so that's why these rates are quite high. In the next slide, we'll look at the dry samples, and it's particularly for dry cattle manure. And you can see the moisture content, dry matter is 16.5% at the bottom of that table on the left. Here, the total nitrogen in pounds per ton is 26.8, but only 10 pounds of that is available in the first year if it's incorporated right away. If it's broadcast and not incorporated for more than 3 days, that drops down to 7.5 to 9 pounds, which is like 30% of what was applied. And there is residual that is available in the second year and the third year, which would be from organic components in the manure that decay and are broken down over time into the second and third year. That represents 10%, 5% later on. The P2O5 and the K2O, basically the guidelines are that for liquid, it's almost all available. For dry, it's mostly available, 90% in the first year, and anything that's not used by the crop in that first year will be residual for the next crop, which you can estimate, but you would only know if you tested it in the soil. The availability of nitrogen, as I indicated, is different in different states. In Iowa on the right and in Wisconsin on the left, you can see that the nitrogen availability that's expected when the manure is sampled, when the manure is incorporated within an hour of application on the surface or injected. For a dairy liquid, it's 50% of the manure is available. And if you look at the green highlight in the Iowa data for dairy liquids, it's 30 to 50% as well, assuming that it's incorporated right away. The difference is significantly wider when you look at the swine manure. In Wisconsin, that swine manure availability is only 65%, even when it's injected right away. Whereas for Iowa, an anaerobic pit swine lagoon sample, that manure nitrogen is available either 90 to 100% that first year if it's injected and incorporated. The reason behind all that is primarily ammonium nitrogen. And the losses from not incorporating it is tied directly to volatilization of the ammonium from the surface, and losses later on would be from transformation of the nitrogen to nitrate or leaching or some other loss through a biological process. Here we have the nitrogen cycle, essentially. Ammonium in the manure is readily available to the plant. It can be taken up as ammonium, or it can be converted to nitrate and taken up. Ammonium can be lost through volatilization. As I said, if it's on the surface, it'll be transformed to ammonia gas and lost that way, or under the surface in contact with bacteria, can be denitrified and then losses into gas, which is a smaller concern, but it can happen. And then in the soil, if it's not retained by the clay, even if it is retained by the clay, it's still subject to action by bacteria, where it's rapidly converted to nitrate in the nitrification process, and that can be lost to leaching as well as taken up by the plant. So it is part of the nitrogen that's applied in a significant part in some manure samples, and I'll talk about that in just a second. When we do the analysis in the laboratory, the kildal nitrogen, which most people know as TKN, it's reported as total nitrogen, and it is correct, but it's only the protein components, the complex organic compounds that contain nitrogen, and the ammonium ions. It does not include any nitrate. That's okay primarily for nitrogen, for manure samples, because most are in anaerobic pits. Certainly all the liquid samples are anaerobic, and there's very little nitrate in manure samples. So it's less than 2% of the total amount of nitrogen that's there. So really saying that a TKN is a total analysis is a fairly accurate summation. But remember, see here that it does include ammonium. And when we look at that, the total nitrogen of the dairy manure that I showed before, you can see that distribution. On the right is a distribution of how much of that total ammonium is ammonia. Total nitrogen is ammonia. And although the scales are different, the scale here on the ammonium side goes up to 50, whereas you can see 50 represents the lower portion of the graph on the left. There's a spike there in the liquid portion of the samples, where a lot of the nitrogen that is present is in the ammonia form. If we look at that proportion of the total nitrogen that is ammonium form, you can see that this is a graph of that relationship NH4 over total N. And it can be anywhere from 100% down to 0% of that nitrogen is in the ammonia form. And that on the very low samples, approaching or even exceeding 100% is not uncommon, because they're two different measurements. And so a little variation in one or the other will give you, although they're both accurate analyses, you can get a more than 100% nitrogen in the ammonium form occasionally, but it's not usually the case. So the average of that is in the 40 to 60%, which then highlights why for nitrogen nitrogen from dairy manure, about half of that nitrogen could be lost. About half of it is in the ammonia form on average. And so while not all the ammonium is lost, some of it is lost through volatilization and then conversion to available forms from the solid portion of the manure sample. For swine manure, as I mentioned, the bulk of the samples are liquid. And for this, in this case, that same comparison of nitrogen as how much of that nitrogen is ammonia, we see that the range is up to and above 100%, down to about 20%. Very few samples are less than 20% ammonia. And the average is anywhere from 75 to 80% of the total nitrogen that's in that swine manure sample is in the ammonium ion form. And that's why incorporation and injection is the recommended way of applying swine manure. And that's also why in Iowa, the recommendation is to wait until the ground is cold. If you're applying in the fall, apply it after the ground is 50 degrees and cooling. And that way the ammonium is retained as the ammonium ion. It's absorbed on the clay surfaces. It's not acted upon by bacteria, because bacteria life slows down at below 50. And so you'll retain that nitrogen over the winter. And then in the spring, when everything warms up, then it starts to be released as nitrate and made more available or to either leaching or crop uptake. So knowing that availability of, or knowing that percentage of the sample that is in the ammonium form is part of that decision or part of that recommendation for how much nitrogen is available initially for year 1, year 2, and year 3 for the different kinds of manure that we looked at. That will wrap up my portion for nutrient management planning. Haley's going to take us through some of that criteria in the next few slides.
Thanks, Jim. We can see from the previous slides that there is a great range in how variable manure can be, from species to how it's handled, from storage to application equipment, and much more. So when it comes to applying manure on the agronomic end, we implement nutrient management plans in Wisconsin. NMPs are regulated by law, like Jim had mentioned, by the NRCS 590 standard and the NR 243 if you're a CAFO, or a concentrated animal feeding operation. Simply stated, NMPs include the following: annual updates, which are updated with crop, fertilizer, manure, and tillage rotations. Soil tests are updated every 4 years or every 4 cropping seasons. Nutrient recommendations based off soil type, and soil loss equation is calculated to make sure fields do not exceed the tolerable soil loss, and that's based off of soil type. And in order to sign off on these nutrient management plans, you have to be a CCA or a certified crop advisor. So there are 2 main limiting factors or reasons why we are focusing on nutrient management planning. The first being groundwater, which is where excess nitrogen contributes to the high nitrate levels in our groundwater across the state. So you can see in the picture to the right, we have from yellow to orangish color. Those are going to be a range between 0 and 10 parts per million, and 10 parts per million is our safe drinking water standard. And these are just the nitrate levels in the drinking water. So once we get above 10 parts per million or above our safe drinking water standard, it turns to that really dark red. And you can see there's several spots across the state that this occurs. So kind of concerning. Nitrogen also contributes to the dead zone in the Gulf of Mexico. As you can see in the picture at the bottom left, the redder the area, the less oxygen in the water. The less oxygen, the less fish can survive, meaning the further those local fishermen are having to travel to find their quotas. As a result of being responsible growers, we want to watch the amount of nitrogen we put on our fields. For soils that are susceptible to nitrogen loss due to soil type or depth of soil, nitrogen is restricted to 120 units of N. The second limiting factor or reason we implement nutrient management plans is to protect our surface or freshwater bodies. And we address this based on soil analysis. Soils with a high soil test P or phosphorus are restricted on the amount and frequency they can get manure applications. So phosphorus feeds the algae that we can see in these two pictures and turns our lakes and rivers green. Some of our soils are naturally high in P, yet farmers are blamed. But also when you think of that typical lakefront property, it's pretty immaculate, right? Well, it's not just water that they're putting on. In nutrient management plans, we document all nutrient applications, whether it be fertilizer or manure. When it comes to documenting our manure applications, we can simply use the book values or the estimated available manure nutrient content based off manure samples that are collected and analyzed from across the state of Wisconsin. Here you can see some book values for solid in the green and liquid in the blue. Right off the bat, we notice two different dry matter contents, the liquid or the dry. Two sets of manure values, meaning two sets of manure values. Next, you can see there are three different nitrogen values, which plays into how a grower handles their manure when it comes to time of application, surface, incorporated, or injected. Next, we can see different animal species, a breakdown of dry matter even further, and finally indoor and outdoor pits. There are so many different factors that can go into accounting for your manure. Considering all these different aspects, plus the variability we saw earlier in the presentation, there is truly something to be said about taking your own samples to see the actual value of your manure, because all farms are different and how we handle and treat a manure is different. We're going to take a look at this on our next slide. So here's an example of what a manure analysis looks like coming from the lab in Wisconsin. We have the livestock type, in this case it's dairy, the manure type, in this case it's liquid, based off of our dry matter content. Then we move down to see the different nutrients being tested: nitrogen, the surface, incorporated or injected rates, phosphorus, potassium, and sulfur. At the bottom, we see estimated value of available nutrients. So this is going to be based off of current fertilizer prices and the nutrient content that you have in your manure. However, the most important section is going to be in the yellow, which shows the estimated available nutrients in the manure for the first year. Again, nitrogen has those three different levels, so make sure you account for that. In order to compare, I took the values from this yellow section and put it in this table. So that's going to be the actual column. And now I'm going to bring up our book values and see that there's a little bit of a difference here for this farm. Major differences, actually. So taking it a step further, let's say we put on 12,000 gallons of manure. So here we have 12,000 gallons of manure with that actual. We get 169 units of nitrogen, whereas if we would have just used the book values, we got 84 units of nitrogen. In this instance, if they had fall nitrogen restricted soils where we're restricted to only have 120 units of N, they would not be able to apply based off of their actual results. Again, it boils down to manure storage and application to even feeding rations, because what goes in must come out. Each of these are unique on every farm. So for CAFOs, annual manure sampling is required. Typically one sample is collected per million gallons or per field, whichever is more often. For manure analysis, dry matter is huge. It determines how we handle the manure and what restrictions we have to abide by. Again, we have the nitrogen, phosphorus, potassium, and sulfur analysis. Like I mentioned earlier, we are worried about nitrogen and phosphorus. We have nitrogen restricted soils, the 120 units for the fall. The second piece we look at is the phosphorus, because we don't want to overload our soils with P due to the surface water issues, which is why we soil test and spread manure on different fields between seasons and years. For CAFOs, we also have to consider second and third year manure credits as well. With all of these samples, a 3-year average is tabulated, seen here, and used in our nutrient management plans. Following through with the manure analysis is documenting where the manure has gone the past year, as well as planning where you want to put it this upcoming year. These items are collected during the annual updates, where we meet with our customers to create a manure plan. Nutrient spreading restriction maps, seen to the right, field verification forms and procedures, manure logs, seen at the bottom, and emergency response plans are all put together, delivered, and explained to the farm prior to application. For example, I would sit down with this farm and make sure that they know that red is an area where they cannot apply manure, and that's because they have a stream here. And then the purple area here is where manure has to be injected because it is within a surface water quality management area, or a SWCMA, due to the 590 standard. With that, I'll have Jim talk about our conclusions.
Thanks, Haley. So in conclusion, it's really just a matter of knowing what you have in your manure. If you rely on book values, you may or may not be applying the correct amount of manure, maybe overapplying nitrogen, or you may be shorting your crop in phosphorus or another nutrient because you don't know what is actually going on the field. So testing the manure is important because of the requirements of crop production as well as the requirements of the law. And then again, it's important to take account of the variable nitrogen over time, seeing the variability that we see in the ammonia content. It's the amount that's available year 1, year 2, year 3 is dependent on several factors, as well as knowing how to sample that and take a good sample, which will represent the value or the cross section of your manure whole sample. So managing that, don't manage it as a waste stream, but manage it as a valuable resource that it is. It's better to know your own data and to use that than to just rely on somebody else's estimates. And from that, you can get a good economic return that's paying you back for your good management practices.
Again, manure is natural, it happens. Use it as a resource, not as a waste material. With that, we want to thank you for enjoying and participating in our presentation. If you have questions that we are not able to answer, feel free to email one or both of us, and I'll turn it over to Catherine to see if we have any questions that we can quickly answer.
Thank you both, Haley and Jim. We have about 5 minutes left for questions, and we did have quite a few come in. So I'm going to try and get through as many as possible. The first question we had come in is, how many days in advance do I need to take/send my sample before application?
Sure, I'll take that one. So when it comes to analysis, it takes about 48 hours once the sample gets to the lab. So I would say give us roughly 4 days. So that way you can take the sample, it gets analyzed, and then you have a day to figure out what you want to do, how to read the results, talk to your agronomist, kind of a thing.
Perfect. Thank you so much. And I think this is going to be a question for Jim. It was asked while you were going over the dairy section in your manure analysis. Is this because of feeding rations or feed ingredients, i.e. phytase? Not sure which slide it pertained to.
Yeah, that'd be the difference in phosphorus availability probably, and I would say yes. Phytase has improved the uptake of phosphorus by the animal, and so it's lowered the amount of phosphate that's coming out in manure. So yeah, that's true, dairy and in swine.
Perfect, thank you. And this question also came in around during that analysis section. I have a John Deere Harvest Lab. Have you validated its ability to measure nutrients versus a lab analysis?
I can't say that we have validated that in Ellsworth. I don't think they have in Bondwell either. I know that it's a good setup. It's a good instrument, and it gives you real-time analysis of the manure as it's being applied. But it is important to have that validated because it's using a global data set, and your data is not global. It's specific and local. So it's important to validate your field and your conditions rather of your manure with that system.
Great, thank you, Jim. We also had a question come in. Producers who practice no-till or strip-till may have a difficult time incorporating manure, especially dry manure. Do you have any recommendations for minimizing denitrification losses from not incorporating the manure?
I don't know if Jim has anything, but I'm sorry to say not really. Yeah, for no-till or strip-till systems, basically it's all surface application. I know for like liquid application, we can use like a little, it basically just pokes tiny holes, so it's not considered tillage. And then you surface apply the liquid manure, so it kind of sinks in, incorporates. But as far as solid manure, I don't know of anything. I'm sorry.
Yeah, I don't have anything to add to that either. That's a difficulty, yes.
Thank you both. The DNR is moving towards a goal to limit fall spreading of liquid dairy manure. The thought is that it could be leaching of nitrogen in the fall. Any thoughts?
That is correct. They are looking to essentially push for 365 days of storage, so that way there is only spring spreading. Nothing has been set in stone yet. I know we work very closely with a lawyer, lobbyist, so it's a work in progress to kind of actually fight this battle.
I will say in Iowa that the liquid swine manure is considered comparable to an anhydrous ammonium application. And so the same rules that apply to a fall application of anhydrous apply to fall application of liquid manure, cold and getting colder, essentially.
Great, thank you. And last question before we're going to have to close out. If 1,000 gallons of liquid dairy manure is applied based on the book values, how much nitrogen is immediately available to move into the soil? Assume soil temps are above 50 degrees.
That depends on the dry matter content, because there's differences in the 0 to 4 and then the 4 to roughly 12%. So off the top of my head, without looking at that graph, I couldn't tell you. Jim, do you have something?
I don't have a number right in mind either, but again, it would be the availability that's reported in first year availability. That includes both some immediately available and decomposable. I would say probably you could go with half of what's available immediately available in first year as available immediately. That would be just very ballpark.
If that doesn't answer your question, feel free to email us.
Great, thank you so much. So like I said, that was the last question we were going to be able to answer. Any questions we didn't get to, we will sure to respond via email. Thank you so much, Dr. Jim Friedericks and Ms. Haley Sand, for your presentation today. And reminder, this webinar is eligible for 1 credit of CEUs under the self-report and nutrient management. Thank you everyone for joining us today, and have a wonderful day.